All right, fluid pressure continued. And move the camera here. So same equation, what we have is pressure is force over the area, P is pressure, F is force, and then we have A is the area. Now what we're going to do is, if you have a container filled with some fluid, if you have some fluid somewhere, and as long as the density of that fluid remains the same, then you don't have to worry about the variations of pressure here because the pressure will stay the same everywhere within this container, including on the walls and in the corners here and so on and so forth and within the fluid. But if you, let's say you have a lake, you may be aware, in fact, you should be aware of the fact that within the lake itself, as you go deeper and deeper and deeper, the pressure increases. If you've ever done scuba diving, you would be aware of the fact. In fact, not even scuba diving. If you've done any diving, if you go a certain depth below, you will feel pressure in your ears. Or for that matter, if you're in, well, anyways. So, so there's going to be a pressure variation. And the reason for it is that as you go deeper and deeper, well, there is a certain variation in the density, although it doesn't amount to much, but it does, and that being something. Now, if I wanted to have, so let's say there's somewhere down here, we bottom out. Somewhere here we have fluid. There's a little fluid here. I want to figure out what is the pressure at this depth. Let's say somewhere here. I want to know what is this pressure here. I'm going to call it P2. Do I want to call it P2? Let me see what I call it. I do call it P2. So I'm going to call this thing P2. You'll see why in a second. So I want to find out what is the pressure here at this depth. To do that, what I'm going to do is I'm going to, let me clean this up a little. So I'm going to get rid of all of these little particles. I'm going to make up an area here. Let's say I have a little plate, like a circular plate. Right here. With a certain area. So we're going to call this area A2. And I could figure out P2 if I knew how hard, how much force was generated against this plate right here due to the water. So I can extend this up a little. And then I can notice that what I have here is this big cylinder of water above that. So I'm going to make this. Here we go. So I have this cylinder of water and all of this weight of the water. This is the weight of the water. That weight is pushing against this little plate. So I could figure out P2 if I could do this weight over a 2. That would be almost true. It would be true if I had no atmosphere here. But as it stands, I also have this entire section of the atmosphere, the weight of the atmosphere that is also pushing against that. So I cannot ignore, if this is a lake, then I cannot ignore the atmosphere. So there is the atmosphere all over the place here. And on the surface of the water, I'm going to have the atmosphere pushing against that as well. And that will amount to me having pressure P1, which is equal to 1 atmosphere. So I have 1 atmospheric pressure at the surface here because what's above the surface is an atmosphere. And so atmosphere is producing the pressure against the surface of the water. And we will approximate this thing with 10 to the 5th pascals. It's not exactly that. And there are some variations in it depending on the weather, so on and so forth. But we'll just run with 10 to the 5th pascals. So what I really need to do is I have to take this equation and I have to modify it. I have to say here plus P1. Right, so I'm going to have some push from the atmosphere plus all of this weight here due to the water against the plate. Well, before I move on with this, we're going to need the following. This water has a certain density. The symbol for density is going to be rho. I'm going to put it up here. So rho is density. And we want it in terms of volume per mass per volume. Yeah, so we want it in terms of kilograms per meters cubed. These will be the units we will use in this class, kilograms per meters cubed. How much mass you have within a specific volume, that would be it. That would be density. And so density is volume as mass over volume. And that means that density times volume is mass. We will use that expression over there pretty often, that density times volume is mass. So you want to get used to it. All right, now this equation here, P2 equals P1 plus weight over the area A2. Let's see if we can modify it a little. So what I'm going to do is I'm going to run weight over A2. I'm going to extend this further. Well, weight is just mg divided by the area of that little plate. That's going to be pi r squared. And there's some kind of the radius here. It's kind of the radius r. That mass in that equation refers to the mass of this whole section of water. So for mass, I'm going to put in this one, rho times the volume of the cylinder times g divided by pi r squared. And let's keep going. Rho stays, g stays. I'm going to pull this out. Rho times g times. Now the volume of the cylinder, well, that's just pi r squared times h over pi r squared. Now what's my h? H is the important thing in this whole picture because h is going to define my depth. So here's h. Depth, and you want it in meters. Area cancels out, and now you have an expression here, rho g h. So the equation for the pressure at some depth is equal to the pressure at some other depth above it, plus rho g h. This is the equation that you will need. So P1 is the pressure of the surface, or maybe somewhere else, say maybe here. And then for that matter, I'm going to give you two variations, possible options here. So let me clean this up because we don't need any of this modeling here anymore. There. If you want P2, then as long as you know P1 and H, the depth, you're all set. Suppose that what's given to you is P1, where P1 is here, then in that case, your H is this, and then you can calculate P2 at the same elevation here. So P1 is any pressure above it, as long as you know what that is. And then H is the distance from P1 to P2. All right. Although you have to stay within the same fluid. Reason being is that that rho, oh, so this is 9.8 meters per second squared. And then this here, that's density, the fluid. If it happens to be water, then I'm going to put here density of the water, that's 1,000 kilograms per meters cubed. This is the constant we're going to use because of the units we want to keep. So kilograms per meters cubed, density of water here is 1,000. That's something you're going to have to remember. All right, let's solve some problems. So I'm going to do problem 3 of the worksheet, and this will do for this whole project. So I'm just going to clean this up. I can rewrite this equation somewhere over there. We don't really need this whole derivation anymore. So pressure P2 equals P1 plus rho g h. All right, problem 3. And it's this worksheet. It's the first worksheet on fluids. What is the pressure at a depth of 10 meters below the surface of a lake? I actually have, here's my lake, and then you bottom out somewhere here, and then you go to a depth of 10 meters. And the question is, what is the pressure at that depth? So here, P is the unknown. Now this is as simple as it gets. You're looking for P2. You know the pressure here, P1. Here, this is a lake. So what's above the lake is an atmosphere. So it's the whole atmosphere pushing down on the surface. Therefore, P1 is just one atmosphere. And that's 10 to the 5th pascals. So I have P1, I have H. I can easily calculate P2. P2 equals P1 plus rho G H. Now, P2 is the unknown. P1 is the atmospheric pressure, 10 to the 5th, plus the density of what fluid do I have here? It's water. So this is going to be 1,000 kilograms per meters cubed times G, 9.8. As long as you're on the surface of the Earth, it's 9.8. If you're somewhere else, that's a different story. Times H, which is the depth, so times 10. And so then you have P2 equals, and you'd have to run this thing through. Let's see what we get. All right. 1.98 times 10 to the 5th. Pascals. Units are pascals. So if this is 1 times 10 to the 5th, and this is 2 times 10 to the 5th, then you're looking at basically 2 atmospheres. So here you have 2 APMs. You have 2 atmospheres at this depth. All right, well, anyways, so this will do. And you should, normally I give students all of these problems to do. So I'm going to say solve 4 through, well, that's interesting, through the second 9, or at the least pick 4, at least pick 4 or 5 problems, and then make sure that you can, that you know what you're doing. Okay, and this will do for this part.